This is a video abstract for the paper Archipov's Theorem, Graph Minors, and Linear System Nonlocal Games by
Connor Paddock,
Vincent Russo,
Turner Silverthorne,
and William Slofstra.
Given a graph where each vertex is assigned 0 or 1, we can make a linear system over Z2, where there's a variable for every edge, and the equations say that the sum around any vertex must be equal to the vertex label.
The resulting system, Ix equals b, is called the incidence system of the graph, and it has a solution if and only if there is a way to assign zeros and ones to each edge, such that the sum around any vertex is equal to the vertex label mod 2.
If G is connected, then Ix equal b has a solution, if and only if the sum of all labels is even.
So the example above doesn't have a solution.
In this paper, we study the incidence group associated to a graph G and a vertex labeling B.
This is defined as the finally presented group generated by variables xe for e and edge of G, along with another generator j to act as scalars from Z2, such that each generator has order 2, the element j is central. For every vertex v, the product over generators of edges incident to v is equal to j to the label of v, and lastly, two generators commute if their edges are incident to a common vertex.
If we required all the generators to commute and replace j with -1, then these relations are just the incidence system of G and B written multiplicatively. The first relations say that the variables have to be plus -1 valued, and the third relations are exactly the constraints of the incidence system.
Since we don't actually require all the generators to commute in the incidence group, what we end up with is a non-commutative analog of the incidence system.
However, we do require j to be central so we can treat it as a scalar. And since there's no specified order for edges around a vertex, we require generators incident to a common vertex to commute.
Our interest in these groups comes from the subject of nonlocal games in quantum information, where there is a graph incidence game associated to any pair, G, B, such that the associated game has a perfect classical strategy if and only if the incidence system, Ix equal b, has a solution, and has a perfect quantum strategy if and only if J is non-trivial in the incidence group.
With an odd parity labeling, the game associated to K33 is the Mermin-Perez magic square, and the game associated to K5 is the magic pentagram.
These are two famous nonlocal games, which have a perfect quantum strategy, but no perfect classical strategy.
More generally, Archipov's theorem states that the game associated to a connected graph has a perfect quantum strategy if and only if Ix equals b has a solution, in which case the game has perfect classical strategy, or G is non-planar, i.e. G contains K5 or K33 as graph minors.
Incidence groups of graphs are a special case of solution groups of linear system games, and in that world, determining if J is trivial is undecidable. We were interested in why it's so much easier to determine if J is non-trivial in incidence groups than in solution groups.
It turns out that if H is a minor of a connected graph G, then there is a surjective group homomorphism between the incidence groups of G and H, mapping J to J.
For example, if we start with graph G and delete an edge E to get a new graph H, then the incidence group of H is the quotient of the incidence group of G by the normal subgroup generated by XE. Something similar happens for the other graph minor operations.
The Roberts and Seymour theorem implies that if P is a property of G preserved by such homomorphisms, then P is characterized by avoiding a finite set of labeled graph minors.
In this paper, we find the minors for the incidence group to be finite or abelian.
Specifically, we show that the incidence group of G and B is finite if and only if G avoids K36 and 2 disjoint cycles. And the incidence group is abelian if and only if G avoids K33 with an odd parity labeling, K5 with an odd parity labeling, K34 with an even parity labeling, and 2 disjoint cycles with any labeling.
We explain how these properties relate to quantum strategies in the paper.
There are many other properties preserved by surjective group homomorphisms, and it seems like an interesting open question to determine the minors for these properties.
For more on this, along with the definition of labeled graph minors and all the citations, please see the paper.